Processing integrity, within the trust services criteria, ensures that systems perform their work accurately, completely, and on time. It focuses on the reliability of data processing from input through output, protecting against unauthorized alteration, omission, or delay. This category safeguards the core promise of technology, that what is entered, processed, and reported reflects reality. When systems execute transactions correctly and predictably, customers trust the outcomes they receive. Processing integrity transforms technical accuracy into a foundation of business credibility, where errors are exceptions rather than expectations. The first pillar of processing integrity is data input accuracy. Systems must validate that incoming data is both correct and authorized before it enters the pipeline. Validation rules enforce the completion of required fields, proper formats, and logical consistency, for example, preventing a negative quantity in an invoice. Only approved users or systems should be allowed to input or upload data, and rejected records must be logged with clear error messages to guide correction workflows. Training users who handle data entry is equally essential, ensuring that human oversight reinforces automated safeguards. Input accuracy sets the stage for every subsequent control because errors that enter early often multiply downstream. Processing completeness guarantees that every transaction initiated is also fully processed to its intended destination. End-to-end reconciliations across systems and pipeline stages confirm that no data has been lost, duplicated, or skipped. Control totals and record counts act as digital checkpoints, comparing expected and actual outcomes. Automated verification routines can monitor batch jobs or streaming flows, alerting staff when anomalies or missing records appear. In a well-governed environment, completeness is not left to trust. It is continuously measured, ensuring that every legitimate input produces an auditable output. Timeliness is another critical dimension of integrity. Even accurate and complete data loses value if it arrives too late to support business decisions. Organizations must define acceptable processing latency for each workflow and monitor adherence to schedules. Queue backlogs, failed jobs, or network congestion can delay critical updates, especially in high-frequency environments such as payment processing or supply chain logistics. When thresholds are exceeded, escalation protocols ensure timely investigation and correction. Integrating these metrics into service-level dashboards keeps operations teams accountable and provides real-time visibility to management. System accuracy and consistency validate that what comes out matches what went in. This includes comparing input and output data sets for alignment and using checksums or hashes to detect corruption or tampering. Dual control verification, where two authorized individuals confirm high-risk transactions, adds a layer of assurance in sensitive processes like financial reporting. Periodic sampling across interconnected systems reveals hidden mismatches caused by rounding, formatting, or integration issues. Together, these checks ensure that data integrity is preserved across its entire journey, regardless of how many systems it passes through. Change control for process logic protects the rules that govern data transformation. Modifications to algorithms, scripts, or validation routines must be formally approved and documented before they take effect. Testing in controlled staging environments ensures that changes work as intended without breaking dependent processes. Versioning of configurations and scripts allows teams to trace the exact logic used at any point in time, a critical element during audits or investigations. Rollback capabilities provide a safety net when defects appear, minimizing disruption while preserving accountability. Strong change management keeps processing integrity from becoming accidental collateral in innovation. Error detection and correction mechanisms form the operational immune system of data processing. Automated exception reporting tools identify anomalies, such as missing fields or failed calculations, and route them to triage queues. Human analysts review unresolved cases and document corrective actions, complete with timestamps and responsible owners. Tracking these errors over time reveals root cause trends, helping teams focus on systemic improvements rather than one-off fixes. By treating errors as signals instead of failures, organizations turn disruptions into opportunities for learning and process refinement. Audit trails and traceability provide the historical backbone that makes integrity verifiable. Every system execution should generate immutable logs linking each transaction to its timestamp, source, and outcome. These logs must be protected from alteration, with access restricted to authorized personnel and retention schedules clearly defined. During audits, sampling from these records demonstrates how data flowed and where decisions were made. The ability to reconstruct events accurately gives both management and auditors confidence that the system's integrity can be proven, not just claimed. Quality assurance and peer review introduce human oversight into an automated world. Reports, calculations, and data transformations should be reviewed by independent staff who were not directly involved in their creation. This separation of duties reduces bias and provides a fresh perspective to catch overlooked errors. Teams can periodically audit formula libraries, transformation logic, or code repositories to ensure alignment with current requirements. Each review and approval should be documented, reinforcing that accuracy is a shared responsibility between humans and systems alike. Automation and control validation bring scalability and resilience to integrity assurance. Continuous integration and continuous deployment (CI/CD) pipelines can embed test automation that verifies expected outputs whenever code changes occur. Periodic checksum comparisons of reference data confirm that static datasets, such as product catalogs or rate tables, have not drifted over time. More advanced systems even feature self-healing or rollback mechanisms that automatically revert to the last known good state when discrepancies arise. Integrating these alerts with operational dashboards ensures that technology itself helps sustain integrity rather than relying solely on manual vigilance. Integration with incident management ensures that detected errors or failed processes are not isolated technical events, but part of an organized response system. Failed jobs can automatically generate incident tickets, classifying severity based on business impact. Root cause analyses and remediation steps are captured within the same ticket, linking technical data to risk management processes. Over time, patterns in these incidents feed back into the organization's risk register, helping prioritize investments in reliability and automation. This closed-loop approach connects operational monitoring to enterprise governance. Evidence expectations for processing integrity mirror those of other SOC2 categories, emphasizing transparency and repeatability. Logs of reconciliations, error corrections, and change approvals demonstrate consistent control operation. Dashboards showing timeliness metrics provide quantifiable proof that SLAs are being met. Auditors often request samples of transaction records alongside corresponding audit trails, verifying that data was processed as designed. Having this evidence ready and well organized turns audits into validation exercises rather than firefights, reflecting a culture of proactive assurance rather than reactive defense. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Vendor and subservice process reliance introduces an extra layer of complexity into processing integrity. When upstream or downstream providers handle part of the data flow, their accuracy and timeliness become intertwined with your own. Organizations must review these providers' evidence of data quality controls, such as reconciliation reports, validation rules, and incident response practices. Contracts should clearly define responsibility boundaries, specifying who monitors what and how issues are reported. Continuous oversight through SLA tracking and vendor assessments ensures that even outsourced or shared processes uphold the same reliability expectations as internal systems. Trust in external processing must always be earned and verified. System monitoring and alerts provide the nerve center of integrity management. Real-time metrics allow teams to observe throughput, transaction counts, and completion rates as they happen. When anomalies appear, such as sudden drops in volume or spikes in rejected records, automated alerts should route immediately to operations or product teams. Anomaly detection models can recognize deviations that might not break thresholds but still indicate subtle issues, such as data duplication or missing values. Regular trend reviews help identify early warning signs and shape predictive improvements, moving from reactive firefighting to proactive stability. Sampling and testing remain classic but powerful tools for validating processing accuracy. By selecting representative transactions, auditors or internal reviewers can reperform calculations independently to confirm outcomes. Comparing expected and actual results highlights discrepancies that automation might overlook. Documentation of these comparisons, investigations, and resolutions provides tangible proof of integrity. Recording completion status and reviewer approvals within audit logs ensures accountability and traceability. These exercises aren't merely for compliance, they build confidence that the system's operations genuinely mirror its design. Change impact analysis prevents integrity drift during system evolution. Before deploying any update, be it code modification, schema redesign, or infrastructure shift, teams should perform structured reviews to assess how the change affects upstream and downstream systems. This evaluation identifies dependencies and potential side effects before they cause failures. Verified rollback and fallback procedures guarantee that if an update goes wrong, normal processing can quickly resume. Tracking metrics such as change success rate or defect rollback frequency helps organizations gauge their control maturity. Each successful release demonstrates that agility and integrity can coexist when governed properly. A continuous improvement loop ensures that lessons from defects translate into progress. Post-mortem reviews following data quality issues identify which validation rules failed, what thresholds were too narrow or too broad, and how workflows can be streamlined. These insights feed directly into refining logic, automating repetitive corrections, or strengthening data entry interfaces. Over time, teams measure the reduction in recurring errors as evidence of progress. Continuous improvement converts setbacks into momentum, turning processing integrity from a static control set into a living discipline that evolves with experience. Metrics and key risk indicators make processing integrity visible and measurable. Typical indicators include error rates per million records, SLA adherence percentages, and the frequency or severity of audit exceptions. Tracking reconciliation closure times over successive periods helps measure how efficiently the organization resolves data mismatches. These metrics serve dual purposes, demonstrating operational health to management and providing auditors with objective evidence of control performance. When monitored consistently, metrics become an early warning radar for emerging risks, ensuring no integrity lapse goes unnoticed. Training and awareness programs translate technical concepts into organizational habits. Staff members need to understand why accuracy and validation matter, not merely how to perform checks, but what happens when those checks fail. Standardizing definitions of error types and reconciliation terms avoids confusion between teams. Sharing real examples of data exceptions and root cause analyses brings lessons to life, while integrating integrity topics into developer and analyst training embeds the concept within everyday culture. A workforce fluent in processing integrity reduces both human error and indifference, strengthening the reliability of the entire system. Common pitfalls in processing integrity usually emerge where governance weakens. Teams may skip reconciliations between data hops, assuming automated transfers always succeed. Validation logic may grow outdated, failing to catch new data anomalies, or alerts may be ignored due to fatigue. Sometimes algorithms are changed without documentation, leaving downstream systems inconsistent. The remedy lies in automation that enforces compliance, governance that requires approval, and culture that treats accuracy as non-negotiable. When these remedies converge, the difference between reactive repair and proactive assurance becomes visible in reduced incidents and smoother audits. Cross-category alignment enhances the strength of processing integrity by connecting it with other SOC2 principles. Controls under CC10 emphasize data integrity. CC8 reinforces discipline change management. CC5 focuses on monitoring cadence and oversight, all of which intersect here. Together, these create a web of assurance that ensures systems remain trustworthy even amid continuous change. Linking integrity outcomes to customer trust metrics, such as complaint reduction or data reconciliation speed, helps leadership see that processing reliability is not a technical abstraction, but a measurable business advantage. Maturity progression in processing integrity mirrors the evolution of other control domains. Organizations often start with manual checks and ad hoc reconciliation spreadsheets. As automation grows, validation routines and dashboards become integrated, providing near real-time visibility. Advanced environments introduce predictive analytics and anomaly detection to anticipate problems before they occur. Ultimately, the most mature systems achieve self-healing capabilities, where discrepancies trigger automated corrections and transparent reporting. At this stage, governance focuses on continuous tuning rather than firefighting, signaling true operational excellence. Evidence automation opportunities redefine how organizations prove integrity. Instead of manually collecting screenshots or logs, systems can export dashboards and reports directly for auditor sampling. Tamper-evident logs and secure APIs allow auditors to query data integrity evidence on demand, improving transparency. Integrating audit queries into reporting pipelines automates artifact generation, saving time and ensuring consistency. Automated collection and storage of these records reduce human error and preserve integrity even during high-volume reviews. In this way, evidence itself becomes part of the automated control system. In conclusion, the processing integrity category reinforces that reliability is more than uptime. It is the disciplined assurance that every piece of data processed is accurate, complete, and timely. From validation at input to reconciliation at output, from monitoring to continuous improvement, each element contributes to a system that earns stakeholder confidence. Evidence automation and metrics transform invisible diligence into visible trust, while cultural reinforcement ensures sustainability. As organizations advance toward predictive and self-healing integrity frameworks, they move closer to a world where data reliability is not a goal but a guaranteed outcome, paving the way for the privacy category and its focus on individual data rights.